Hello, Chemistry TED HH students. This is Mrs. Ottman. We are on video number 13, Atomic Structure and Periodicity, Part 6. This is the last video of chapter number 7 in the 10HH class. I come back to it in AP Chemistry, but this is the last of it you'll see for a little while. We're primarily going to be talking about electron configurations again in this video, just more information about them, and we will shorten them. Pause here. So in general, you always want to have the lowest energy configuration for an atom. That's, we know from the Aufbau principle, you always start at the lowest energy level and move up to the highest. But one of the other factors is that you will usually want to have an electron configuration has the most unpaired electrons, meaning the most number of spin up electrons that are not in the same orbital, also with a spin down electron. So what that really means is that if you can have something that has up to 5 electrons, in the D shell, it really doesn't want to have a 6. Let's take a look at some applications with this. Pause here. So we're pretty familiar with the electron configuration for Fe2+, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. So if you take a look at this, the 3d has 4 unpaired electrons. But one of the applications of Hund's rule is that oftentimes one of the electrons from the 4s orbital will move to a 3d orbital such that instead of having 4 unpaired electrons, I now have 6 unpaired electrons, 1 in the 4s and 5 in the 3d. While this could really happen anywhere, the only time that we're going to discuss it in this class will be electrons moving between s and d orbitals to have more unpaired electrons. So it can occur in other circumstances, but for this class, we're going to focus on movement between the s and the d. Pause here. So as you were doing the problem set for the last video, you were probably thinking, man, I would really love for these to be able to be shorter, so I feel like I'm just writing 1s squared, 2s squared, 2p6 over and over again, and it can be shorter. So we already know that the outermost shell is called the valence shell and the inner shells are called the core electrons. And then since the core electron configurations don't vary, we can actually shorten the electron configurations by just representing the valence shell with the symbol of that noble gas in parentheses. So for example, I replace 1s2, 2s2, 2p6, 3s2, 3p6, which is argon in brackets, and then I showed the valence electrons that occurred afterwards. Pause here. All right, I'll work through these. So I'm going to start with Cr with a 5+ charge, so pretty high charge. Take a look at my periodic table. I've got argon. And then after argon, I have 4s1. So normally I would do 4s2 and then 3d, 1, 2, 3, 4, but because of the 5+ charge, I removed those electrons. Okay, now I've got Fe3+. So iron is coming after argon as well. So 4s squared, 3d, 6, but then I subtract 3 to get 3d3. Oh, but I'm not actually finished because I can transition electrons around. Whether you write 4s0 or just leave it out, either way is fine. I make that 3d5. Either way is fine. I typically do include the 4s0 in there just to remind myself where I got it from. And now for Br-. So bromine comes right after argon, just like the others. And then bromine would normally end with 4p5, but I actually make it 4p6. And some of you are probably wondering, could I just leave it as Kr? And while that's not technically wrong, we do typically try to list that whole outermost shell. That's really just the way that they ask for it on the AP exam, so that's why I like to do it that way. Oh, my mistake. I thought there was another slide. I was wrong. Thank you so much for watching. Have a lovely night.